Okay, welcome to Discrete Maths course, which we call here Mathematics for CS 1. So 2 is logic and 3 is probability. Okay, so we'll try not to overlap this syllabus with those. Those are half courses. This will be a full course. There are many TAs whom you can contact. So there will be extra classes plus quizzes on Saturdays. So right now you don't have any class scheduled on Saturday 12, right? Saturdays are free in your schedule, yes. So we'll maintain 12 to 1, which is the time for Monday and Thursday. Okay, the same time. The dates I will tell you as we get closer. So generally we will have class lectures of around 60 minutes. So overall I think we will be able to cover 40 hours for this course that we are expected to cover in the semester. Right, so your semester ended a few weeks ago, right? You just finished the semester and the other one has started. Yeah, so you are exhausted, but we can't help. It's IIT, you have to work hard, especially in pandemic years. But anyways, welcome to in-person classes. So what is this course about, right? So the topics covered here will be basic math, but this will not be a math department course. The difference will be that here we will talk in mathematical formalism, but almost all the examples will be related to computer science. Okay, they'll be very discrete examples and things that appear in both theoretical computer science and practical computer science. And especially when you analyze algorithms, many of these concepts appear. In fact, even not just analysis, but even for design algorithms, many of the concepts actually you need from this course or the topics that we'll cover. So hopefully you will remain motivated. Should not become too theoretical, but it may become challenging after a few months or few weeks. So these are useful in computer science theory, but also systems, which is especially in modeling problems, and general applications. Okay, applications as in data analysis or ML or whatever will not fall in theory and systems, even their concepts from here will be useful both in designing and analysis. So let's talk about the grading policies. So we will have basically 4 components. There will be assignments, quizzes, midsem, endsem. So assignments will be 4 and quizzes will also be 4. Basically, every month you will have something. So you will have a quiz and you will have an assignment. You will have enough time for the assignments. If possible, don't copy. And necessarily, the assignment has to be written in your language. Okay, even if you have discussed, the language between 2 students should be different. If it is not, if somebody finds out, and we have many TAs, somebody will find out, then there will be penalty. Okay, there will be disciplinary action. So try not to copy. I know it's very hard to avoid that temptation. When you have 6 courses, you would want to copy, but learn from now not to. Midsem of course will be 1, endsem will be 1, and the percentage distribution we can have it 15% for assignments, 35% for quiz, 20% and 30%. Okay, so I mean if you perform poorly in midsem or endsem, then still you have 50% distributed across assignments and quizzes, and vice versa. So you should be able to, I mean if you are sincere, you should be able to do well in this course. There are enough options. It's not just exam weighted. So yeah, any questions about this at this point? You understand the grading policy, you understand the extra classes, and the quizzes will always be in extra classes, okay, so that we save time here for teaching. Because the quizzes will be for the whole class. These will be 50-minute or 45-minute quizzes. So we'll miss the whole class, so it's better we have it in the extra classes on Saturdays. Midsem and endsem of course will be as scheduled by the DOA. We'll not change that. So okay, so let's now give an overview of the topics and the subject. So what is discrete maths? Okay, so discrete here will refer to studies where the functions are not continuous, okay, and the numbers are not continuous. So like instead of talking about reals, we'll talk about integers. And instead of talking about functions over complex, we'll generally talk about functions over numbers. Okay, so that there is no differentiation, there is no integration. Okay, this will be a study which is relevant to computer science because computers can only store finite information. They cannot even store square root 2 completely, right? So everything is ultimately just an integer. Even the signs actually are stored in a different way. So computer will not understand -1. It will actually just understand 1, and then the sign will be a different operator. So really, you only store 0 and 1, right? Everything else is done in an operator kind of way. So ultimately, the problems and the solutions have to be very discrete if you want to implement them on a computer. So discrete objects and structures. That's the meaning of this keyword discrete. And discrete basically means that they are refers to 0, 1, integers, and anything which can be stored in finite storage. Okay, so generally we would say that square root 2 is kind of not discrete, although there will be a way to see it as discrete, but square root 2 and e and pi, these are things which are kind of not discrete. The numbers are discrete, so integers are discrete. And so then ultimately you can also see it as some kind of counting which you are doing. Okay, that's counting will be a major topic in this course. Another way to say this is that elements will be countable. So maybe you know already, but can you give an example of an uncountable set? versus a countable one. Right, so we'll not go into the definition, it's not very important for the course, but just as an example, real numbers are uncountable, while integers, they are countable. The difference is that any set which you can find a bijection to integers is called countable, and if you can show that there is no bijection, if there is a proof, you can prove that your set S is not in bijection with Z, then the set S is called uncountable, which is the case with reals. Okay, there is a cute proof. You can do it as a fun exercise that real numbers and integers are not under bijection. Okay, there is no bijection, which means a map which will associate with every real and integer, and vice versa, that map doesn't exist. So in this sense, although both are infinite, still reals are somehow more infinite. Okay, and there is a quantitative way to do this. So those kind of things, if you have not seen, we'll probably be seeing it as examples. And that is a difference between discrete versus continuous. Right, so why do we study discrete? That's, as I said, comes from the way computers work. Because computer storage is ultimately a 0, 1, which is the same as off and on. Right, so just because of this, it's kind of a proof that computers cannot work with continuous concepts. You can approximate continuous concepts in an actual computer, but not exactly. Okay, so this is more for us to think and design and analyze than actually what the computer will do. The computer will always do only discrete things. Okay, so yeah, so let's now go into more specific topics that we'll cover. So the course will have five kind of disjoint chapters or topics. Well, they are not exactly disjoint, but we'll present them as disjoint. Obviously, in your exams and in your quizzes and assignments, we'll mix everything so that you don't know which concept to apply. But in the class, we will make it look very disjoint. Okay, that will be your challenge, to use everything in one problem. So these will be. So we'll not spend too much time on proofs, because that is really a subject in logic, which is anyways a course. And especially since you have passed JEE, so I don't think you need a definition of proof, but still to remain formal, we will name the proof methods, and we will also discuss some examples where, if you are not careful, it may seem like a mathematical proof, but it is not. Okay, so that you are warmed up. So it is important for your assignments and for the exam and quizzes that you write in some amount of formalism. Okay, if everything is hand wavy, then you will lose marks, and also you will make mistakes. So which is why some degree of what we mean by a mathematical proof is necessary, and examples we'll give. Second will be combinatorics or counting. Actually, I will go into more detail now once I've listed. Third will be graph theory. Fourth will be number theory. And last topic will be abstract algebra. So I'm sure almost all these, all these topics you have done for when you were preparing for JEE or for Olympiads, but hopefully you will see new examples here. Okay, so yeah, so in proofs, so what is a proof, right? This is proof is basically you can think of it as a sequence of statements to such a level, a detailed level, that next statement follows from the previous statement almost trivially. Okay, so the way math works is you write a proof where every statement will follow from the previous one trivially, but then you will reach somewhere which will be very, very non-trivial. Okay, so if you can divide your the problem whose solution you have presented in such simple statements, sequence of this order of these ordered statements, such that from statement I to statement I plus 1, the connection is trivial, then you say that you have a proof. Right? So when you reach I equal to 1000, the 1000 statement, something very non-trivial has happened. Right? So that's the job. And in that sense, it is the same with programming. Right? When you write a program, every step will be very simple when the computer executes it, but ultimately the program will be solving something which is very, very difficult, right? Which a single person cannot manually do or cannot even think of how to do. But then a program divides into very, very simple steps, almost trivial steps. From previous step to the next step, it should be trivial. It should just be that the computer takes from register 1 a bit and places it in register 2, right? And then picks something from register 2 and flips it. So that is the level of detail which is trivial, but the combination of these trivial things is something very non-trivial. Right? So that's the level of detail. Of course, if you actually write in your assignments this level of detail, we will not be able to check it. It will be very, very tedious, right? So you have to make a balance that you give the proof idea first, and then you give some details, but you don't give all the details, because all the details will be too much. Then we can't really spend time and check it. So it's a game you have to play. But anyways, to define proof, that's the definition. So it's basically a sequence of steps or sequence of statements, I should say. Steps will be in a program. It's actually the same thing. So a sequence of statements such that the next one follows from the previous one in an easy way. Yeah, so now it's not easy to define what do we mean by easy. Right? What is the meaning of from statement 1 you can get to statement 2? So it can be something as simple as in the previous line you had written 1 plus 1, and in the next one you say 2 equal to 2. Right? So if you say that, what is the transition? How did you deduce statement 2 from statement 1? Why is 1 plus 1 equal to 2? So that is called an axiom. Okay, it's an axiom that this object 2 that you see is successor of 1. Right? So this is, it's not a deduction, it's actually an axiom. So either you go from statement 1 to statement 2 using an axiom, or it may be something which somebody else has proved. So maybe in a book there is a theorem that says statement 1 implies statement 2, and that you can then, when you see statement 2, from that you can deduce statement 1, you can deduce statement 2, invoking the known result, right? So which is like calling a subroutine in your program. Somebody else has implemented the subroutine, you just call it. So either the transition is an axiom, via an axiom, or it is via a known result which has been checked. Yeah, or so there are many ways. We will discuss that more when we actually do this chapter on proofs, but hopefully you get the idea what a proof is. Now many times, just to fool the instructor, you will write that statement 2 follows easily from statement 1, right? So that is not the definition of a proof. Okay, you cannot use terms like easy or obvious or clear unless you also specify why is it clear. So usually it is meant that it is clear because it's an axiom. Then it's fine because we agree with the axioms. But if you are using a known result and saying that it's clear, that is not allowed unless it was done in the class. Then you don't have to copy the whole thing. Yeah, but you cannot just, or you cannot just refer to internet and say that this is given in the internet. That is not a proof. Then you have to write the whole proof. Whatever is there that somebody else has proved, you have to actually have to reprove it to actually justify that you have proved the theorem. The other thing here is that this sequence of statements is not unique. If you want to show some big result, there may be many ways that you can prove it, right? So this is a highly non-unique process. In the same way that if you want to solve a problem on a computer using a C program, different students will write different C programs. Not just, I mean, syntactically, but also the logic and the algorithm and the intuition, everything may be different. Right? So there are many proofs and there are many programs. And you should try to do it your way. That's the whole point. So you used to probably copy codes in ESC 101, and you will probably also copy proofs. But ideally, you should be doing it yourself. So if you did not copy, then it is just impossible that two students submit the same proof or the same program. They will not even look syntactically the same. Okay, there will be deeper differences. Not just syntactic differences, but there will be deeper differences in the order of statements and in the ideas and everything. So that is what we expect. So proofs are not unique. And one of the key aims or goals you should have is reprove things yourself. Okay, just like you write programs on your own, that is how you will learn. So yeah, this what we will do in the first chapter. In a bit more detail, we will see the definition of proof, but also what are the different techniques to prove. Right, so for example, as I said, you may be invoking axioms while transiting from one statement to the next. Or you may be using induction. So induction is this, I mean, we'll obviously see more examples, but as you already know, just to formalize, induction means that in statement 1, you have shown that something is true up to j, and in statement 2 you have shown that if it is true for j, then it is also true for j plus 1, and in statement 3 you reduce that it's true for j plus 1. Okay, so when you have this kind of a logic in your proof, then it's called induction. And obviously induction may not just be on j, it may be on many parameters, right? So it may be on j1 and j2, both of them are changing, kind of a for loop, double for loop in C programming. And it may not be forwards, but it may also be backwards. So you go from j to j minus 1, right? So there may be forward induction, reverse induction, and multivariate induction. So all those things make the proof more complicated, but it's a valid and it's a very important strategy. Similarly, implication, which I actually just used. You show that A is true, then you show that A implies B is true, then you deduce that B is true, right? That's implication. And what else? What else do you remember? Yeah, contradiction is obviously a very clever method, because here you assume that you say that suppose A is true, statement A is true, and then you do some jugglery, you have a sequence of statements, and you deduce that negation A is true, not A is true, right? So if both A and not A are true, then you say that the assumption was false. That's a very powerful technique. We'll see some examples of it. Yeah, examples of wrong proofs. So proofs which are very intuitive but wrong. And students are experts in this, right? So if you are a clever student, then it will many times happen that you will have a strong intuition and you will consider it to be a proof, but then you will never actually find the proof, right? So these kind of statements have a name. Do you know what? Sorry? Yeah, so such happenings are called conjectures. Because of your strong, I mean, if you are clever and if you have experience, then you will have a strong feeling that it's true, and in fact you may also think that you have a proof. So these things are called conjectures, and you can formalize the statement and you can state it as a conjecture, but when you actually write down the proof, you see that there is a mistake, or that there is a gap because you thought that it is clear or obvious, right? So conjectures are very important to make progress, but then you have to be aware that it's a conjecture and it's not a theorem, and certainly not a proof. Yes, and finally there is a important thing. I don't know how much we will do this, but can everything be proved or disproved? So what do you think? Oh, you already know. No. How is that? What is the example of a statement which can provably neither be proved nor disproved? So you have to give a proof that this statement is neither true nor false, or it can be true, it can be false. It doesn't matter. It's a belief. How can you give a proof? Sorry? No, it can't be that easy. But yeah, it can be done. We'll see whether we cover that in this, but certainly a curious question whether if we think that proofs are so important, can everything be proved or disproved? Right? So how do you? So proof is that you give a sequence of statements, each transiting in a trivial way. How do you disprove a statement? Sorry? Right. So I mean, somebody gives you a proof, you can find a mistake in the proof, that is just saying that this current proof is wrong. It doesn't mean that the statement is wrong. If I want to show that the statement itself is wrong, then I have to give a counter example. Right? So counter example is also an important thing. Yeah, and for this audience, I think it goes without saying that you cannot give a proof by an example. Right? If there is a statement, say even plus even is even, right? So you cannot give me a proof that look, 2 plus 4 is 6. So even plus even is proved, right? That will not sell. It will probably give you 0 marks, if not negative, because counter example is a powerful thing. It immediately kills a statement, but example doesn't survive. I mean, it will not mean that the statement is true. It is just saying that, well, in some cases the statement is true, right? Not in all cases. So again, you can compare this with programming. If you are given a problem in ESC 101 to solve, you cannot say that I have hard-coded an input and my program reads that hard-coded input and gives a hard-coded output. So I have solved the problem, right? Your program has to work on all inputs to claim that the program is correct or meaningful even. So similarly here also, if you want to say that you have a proof of the statement, then you have to do something which makes the statement true in all possible cases, which is infinitely many cases all the time. So yeah, example is good, but very weak compared to a proof. Yeah, next topic, let's then move a bit faster. So next will be combinatorics. Yeah, so this is nothing but the art of counting. It's as discrete as it gets, because ultimately the answer that you want has to be a count, which means it has to be a positive integer, right? And this you do a lot in computer science. I mean, if you want to, for example, analyze how many steps your algorithm takes, that's a count, right? How many seconds it takes, it's a count. And then how many possible inputs are there on which the answer is yes, your algorithm works, it's again a count. So different structures we will count, and I'm sure again these methods you have already seen. So let me then just directly go to some examples, not spend too much time on defining this. So the thing, okay, one point here is that combinatorics questions seem like puzzles. That are seemingly unrelated. Okay, so this you may not appreciate, but when you compare it with the other areas that I will talk about, the other areas always have some central problem which is solved, and then everything else is kind of a corollary of that. That is generally not true with combinatorics. So here the results will seem unrelated and they'll be solved by different methods. And there is really no central question. It's a bit similar with probability also, that it's more of a tool and a collection of puzzles. So the more examples you have seen, the more expertise you will get. So yeah, so now just to exemplify that, So puzzle number 1, for example, is for any n, let me use this notation. Okay, this will always mean for all n, for all positive integers n. There exists, so this notation will mean there exists integer, positive integer, in 0, 1 digits. Okay, so it will not use the digits 2 to 9. So there is a positive integer in 0, 1 digits that is divisible by n. Is the question clear? It's kind of a random question, right? And these are the kind of questions we will see in combinatorics, these kind of examples. And the way you will do it is by counting and by using clever tricks. Do you know a proof of this? Okay, only one person. The others will see the proof when we do it. Okay, next is, what is the number of ways? This notation will mean number, count. So what is the number of ways to distribute n balls in m bins? Right, this is a counting question which you have seen in many, many forms. Right, the balls may be distinct, the bins may be distinct, or the balls may be identical, bins may be distinct, and so on. Right, all these possibilities are there with pretty non-trivial ways to count, give the answer. Similarly, you have seen an example on permutations. So count the number of permutations. So let me just continue with that. Number of ways to permute 1 to n. The set having numbers, integers 1, 1, 2, 3, dot, dot, n, such that every element is moved. No element is fixed. Right, so these are called derangements, right? So this also you have seen how it is done. We'll do it again. So how many ways is there to permute numbers such that none of these numbers are fixed? So for example, 1 should not go to 1, 2 should not go to 2, dot, dot, n should not go to n. Everything should be moved. Similarly, number of ways to parenthesize. So parenthesize statement, how many valid parenthesize statements are there? Using the opening bracket and the closing bracket, right? So for example, so when you open, then after a while you have to close, and between that you can again open and close. Right? But you cannot do that, these things will not be allowed. So you open and then you close only once, right? Or you again open. So this, for example, is not allowed. So these kind of basic things, but then how many, so if you have n brackets, how many valid and invalid statements are there, right? So you must have seen these kind of questions also. They basically, you use what to find this? No, in general the method is recurrence. Yeah, you write down a recurrence and then get, for example, the generating function. Those examples we'll see. So using n open and n closed brackets. So find the function of n. So those are the generic techniques. And we'll try to give or see many examples in the class and then in the assignments. Okay, so maybe should jump to the next one. So next is graph theory. So graphs may mean two things. It may mean you are looking at the graph of a function. That is not what we'll do here. By graphs, we'll just mean that you have such diagrams like this, and you connect them with edges. Okay, so these pictures, we'll call them graphs, and there may be, these edges may be directed or undirected. They may be labeled with some number or unlabeled, weighted or unweighted. The vertices may have labels or may not have labels, so all these things. This is a very versatile concept or a way to represent data and questions to model questions in computer science. Almost any interesting algorithm which you will write, thinking about those algorithms and their analysis in terms of graphs will be of help. Okay, so what we will do in this course is more on the mathematical side of it, which is properties of graphs we'll study. There are a lot of algorithms in graph theory which you will do in algorithms course, and some of these you must have done already. Well, not too much, but you may have seen it in ESC 101, right? You have just started your second year. So the only computer science course we have done is the programming course. Did you see graphs? Yeah, okay, fine. So you will see it in algorithms then, or if you do data structures and algorithms. But the math part we'll do here. So these are combinatorial graphs. But generally we'll skip the term combinatorial. It just distinguishes these graphs from other terms in math like graphs or diagrams of functions. So the representation will always be like this: vertices, edges, and maybe other associated data with vertices and edges. Right, so this is very versatile. It models in computer science networks, like, it can be in communication, which means that you can think of the vertices as, let's say, routers or machines, and the edges you can think of as either they are wires which are physically connected, or it may also be simply a channel as a wave. Right? So it can be anything, but then we model it as a graph and we try to study the properties of the graphs, or we do algorithm on this graph, and from there we learn about the actual practical problem that you are modeling. Or it may be coming from transportation example, in which case vertices are cities and edges are just roads or railway tracks, or again, they may be abstract. For example, between cities, you have a plane flying, right? So that path is not a fixed path. It keeps changing, but approximately it's an edge, right? So this graph may represent anything. It's a very, it can abstract any practical problem. So for example, to the extent that it can also be a social network, right? So you may be in the center of this graph, and every edge basically shows who you are related to. And if you are related to person X, then person X may be related to Y. Again, you have an edge, right? So internet, for example, is a great example, which is a giant graph. And in fact, whenever you are doing Google search, there is a graph algorithm which actually works. Okay, it's a probabilistic graph algorithm which searches for your keyword in that big, ever-growing internet graph. We do that in probability. It's a very nice example, probably the most important one these days. Okay, so yeah, so this is unlimited number of applications and modeling. So what we will do is, some properties and some problems. Of graphs seen abstractly. So for example, is there a way to go from city X to city Y in a graph such that you visit every other city once? Right, so it seems to be an artificial problem, but it's a central problem in algorithms, and it was shown that it is very hard. It's impossible to solve practically. Okay, as the size of your graph grows, let's say there are n cities, and there are these connections given in an arbitrary way, and then you have the source X and you have the destination Y, and you want to find a path. So first of all, finding a path itself is an algorithmic question. That you can do easily. You can also find the shortest path if given distances. All that is easy, but this is not that question. This question actually wants every other city to be visited exactly once, right? So whether such a path exists or it doesn't exist, and deciding which way is a very hard problem. Okay, if you try to code this, the only known way currently is brute force, which is you from X to Y, you try all possible permutations. Okay, from X you say that, okay, I'll go to city Z1, and then is there a path from Z1 to Z2 and so on. So it's basically a permutation. Your path is a permutation of the other cities. You try all possible permutations. And how many permutations are there for n cities? N factorial, right? So n factorial is close to n to the n. It is definitely more than 2 raised to n. So if you tried this, then on 50 cities, it's already 2 raised to 50, right? So it gets impossible to solve in practice. So you want to give an answer 0, 1, yes, no, but you can never find it in practice because it's just, the algorithm is too slow. So these are very special problems. They are practically impossible to solve. They are called NP-complete or NP-hard. These are hard problems. So this in particular is an example of Hamiltonian path. right? So you should be careful of practical problems which can be modeled this way. If you're trying to find a Hamiltonian path, then it's impossible to do in practice. You can only do it manually for small graphs, but you cannot do it for large graphs. If you haven't seen this, it can be a bit surprising. And yeah, other question which is relevant to you is, suppose you are given a set of boys and set of girls. And as usually happens, each boy has a preference, I mean, of girls, maybe also boys, but here we only look at preferences of boys in girls and girls in boys. And then you want to find a matching such that it is in some sense stable. Okay. So basically you can also represent this as a graph. So boy 1 has these preferences and boy 2 has these preferences, and similarly girls have preferences. And then you want to basically find, so if you number these 1, 2, 3 to n, so again you basically what you want to find is a permutation that boy 1 should be mapped with, let's say, girl pi of 1, and boy 2 should be matched with girl pi of 2, and so on. So again here the problem is that number of permutations is too large, it's n factorial, right? So again, if the number of boys and girls is 50, then we have to go over 50 factorial, which is much more than 2 raised to 50. So it's practically, it seems impossible. So that's the problem of matching. But it will again be surprising that this problem can be practically solved. Okay, so although the solution space is so large, as it was in Hamiltonian path, still there is something special in this graph that can be utilized. Okay, so this abstract graph is very different from the graph in the Hamiltonian path somehow. It is not immediately visible, but there are famous algorithms that will find you a matching such that somehow it is stable. So this also we actually do it in advanced algorithms class. Have you seen this algorithm before? Yeah, so there are fast algorithms. In fact, you have been a guinea pig for the algorithm because you gave preferences for institutes, and then ultimately you were matched, right? So that matching is also a very complicated task because there are way too many Indian institutes and way too many candidates, and each has a preference. So if you look at the preference matrix, it's huge. And then a matching is found out so that nobody can question the matching. It's a stable match. And the secret is that it is designed in a way to keep the students happy. Okay, so similarly here there is a way to keep the girls happy or the boys happy. And based on who you want to keep happy, you can design this algorithm. It works fast, it finds a match in the way the stability is defined. Okay, so yeah, but we'll not do matching, of course, in this course because that's algorithm. We'll just, this graph is called bipartite graph because it's in 2 parts and there are no edges inside these 2 parts. The edges are only across. So it's called the bipartite graph, and there are nice properties of it which we'll study in the course. There are 2 more topics, so let me be very short on these. Which one is this? This is the 4th one. So 4th topic will be number theory. So number theory, as it suggests, is the study of numbers, which is basically integers, positive integers even. and it's the earliest branches of mathematics. Why is it the earliest? It's the earliest because numbers were invented first, before you invented matrices and fields and rings and so on. And it's also easy to see on your hand, right? You can count on fingers. So this was the first thing that was invented, and once it was invented, the questions are very easy to ask about numbers. But as great mathematicians have learned over the millennia that these simple questions which are asked, they are very difficult to solve. Okay, so this is an area where questions can be asked very simply, but they are very difficult to answer. It may take a lot of other machinery to actually answer questions here. That will be a feature of this. So easy to ask, but difficult, hard to answer. So easy to ask means that the notation is very simple. You are just asking, for example, whether, for example, this even plus odd is equal to odd, or even plus even is equal to even. Right? So these are simple to ask questions. You don't need too much of definition. And similarly, whether there are, I mean, in how many ways can you factor a number? You can ask this, right? Like 6 is equal to 2 times 3. So you can define factorization immediately, and then you can ask questions about factors. You can ask questions about prime numbers. So you can ask how many primes are there. Do you know this? Do you know their count up to x? What is the density of primes from 1 to x? So we will give those estimates. Yeah, the density is 1 over log x, roughly. So between 1 to x, you have x by log x primes. But even before that, to show that prime numbers are infinitely many, this is an interesting proof. That's kind of the very first proof that people found which goes via contradiction. Right? So it's a proof by contradiction that primes are infinitely many, and then there is a more sophisticated, clever proof that we will see, which gives the estimate even in an interval, like 1 to x, how many primes are there. So these kind of questions. This is very important in computer science because almost all of cryptography and error correcting codes is based on number theory. So you may not have heard about error correcting codes, although cryptography is easy to believe. But error correcting codes is something which makes the computers work. If error correcting codes were not there, then computers could not work in practice. Because what happens is that in storage or in communication, there are always errors. Right? So when you send, let's say, inside the machine, when bits are being transferred from one location to the next, many of the bits, they get flipped simply because it's a physical device and there are errors in it. It cannot be foolproof. And so using these erroneous channels, still you have to do exact computation. Right? So that's a problem that you have to solve first mathematically. If you cannot solve it, then you cannot actually create a machine. Right? So this was a problem which was solved in early 1900s before any kind of physical implementation was done. So it was solved by designing these error correcting codes, and that is some major application of number theoretic ideas, and something from algebra, which will be the last topic. So, yeah, so what will we do there? We'll do a lot of things, but let's skip all that for now. So we'll basically focus on abstract operation instead of so you are used to adding, multiplying, dividing, or subtracting numbers. So instead of doing it on numbers, we will say that we can generalize it, and then we can see these operations as abstract. Okay, so we'll define these objects like groups and rings and fields and so on, which will in the beginning seem a bit boring because we are unnecessarily adding more definitions. But it will be very powerful in the sense that you will find proofs which will apply to many objects simultaneously. Okay, instead of proving something for positive numbers and then reproving it for reals and then reproving it for matrices and so on, we can actually then be able to give proofs which hold for all these objects simultaneously. So that's the power of algebra. Common proofs across structures. And the other thing is it can make statements more systematic. Okay, so for example, you can give for a geometric statement, you can give a geometric proof, or you can give a proof via coordinate geometry. And the first proof will be more intuitive and easier to read. And if you use coordinate geometry, then it will be more symbolic. But that somehow is better for computers, right? It becomes more systematic, and potentially you can implement that algorithm a bit easier. So this example is about going from geometry to coordinate geometry. Yeah, so this is a silly example, but this kind of more systematic thinking and more abstract thinking is what we will exemplify through better and more specific examples. So that's a quick outline. So next class we'll start with proofs.